Good morning. Welcome to Krishna's classroom. Now we introduce the concept of Lebesgue integral for general measurable functions. Now, if you recall the various steps we have traced in this endeavor, we will see that the first thing that we did was we defined integration of what are called simple functions. Then we proceeded to the next level, namely second stage. We defined integral of bounded measurable on sets of finite measure. So the second stage was essentially to work on what are called bounded measurable functions and defined on sets of finite measure. So that is the second thing, and we went beyond simple functions. Simple functions have all these properties. The third stage was to integration of non-negative measurable functions so we went one step further, except that we paused a bit by working only on non-negative functions, which I have explained earlier why we do that, and once again I will be talking about it. And now finally the fourth stage is to work on what are called general measurable functions. So stage by stage we have removed restrictions, and now we are coming to the general scenario. And what we have done is, in this process you see that we defined integration of simple functions. Then we approximated bounded measurable functions on sets of finite measure by a sequence of simple functions, and then we used the limiting process to define the integral. The third stage was approximating non-negative measurable functions by bounded measurable functions on sets of finite measure. Here we have not assumed that your function is defined on a set of finite measure, could be on the whole of R, okay, or some unbounded measurable subset of that. All these are possible, but then we have successfully approximated every function of this class from the class using the class of functions in the second considered in the second stage, and then of course we use the limiting process. Now the final stage is, see, we have done most of the work. The final stage is use this non-negative measurable functions and their integrals to define the integral of general measurable functions wherever it is possible. Okay. So that is the strategy. So these are all through approximations. Approximation and limiting process, approximation and limiting process. Here, of course, writing up a general measurable function as a sum of two non-negative measurable functions. This is the strategy that we are going to use. Okay, so that is just a brief recall of the various path we have traced. Now let us come to that point. Now we consider the case 4. So we take f from a measurable subset of R to R star. R star is which is equal to that is the extended real valued space, and we are talking about functions with extended, which takes extended real values only. Now of course E is contained in so we define, it's not defined, we have f plus or fx equal to where f plus x equal to maximum of zero, f minus x is defined as maximum of minus fx 0. Okay, I mean these are well defined. It could be when you take the maximum. See, this could be plus infinity. So f plus may take f plus and f minus may take value plus infinity also. And then you see that fx is equal to this. That's quite easy to see. Now you can, if you want, you can look at the graph again. I have done it several times. Suppose as an example, this is the interval. Now on which the function f has a graph something like this. Okay. Then what happens is your f plus is on this set it is going to be f itself, and on this portion it is going to be this, and on this portion it is going to be this part. So the function is now this is the graph of the function f. Okay, I think I better. Now what about f minus? F minus is the maximum of minus fx and 0. So if you take minus fx is going to be this. It's a reflection of f over this line. So you get here its reflection, and here the reflection will be something like this. This is the reflection. Now you are taking, this is minus fx. That's the graph of minus fx. Okay, so the graph of minus fx is something like this. This is minus fx. Now we take minus fx, maximum of minus fx and 0. So that is going to be marked with a different color. You have 0 all over here, and on this portion it is going to be this one, this one. So this is going to be minus. So f minus and f plus are both non-negative functions. Now you can easily see that fx is equal to, for x belongs to, okay. Now there is a problem, except at points where f plus x and f minus x are both infinite. Oh no, there is no problem. No, no, there is no. It's fine because yeah. So fx, f may take the value I better write it here. So let me plus infinity at it is possible. Okay, so that is a caution that we want to make. So wherever f plus x is positive, then f minus x is 0. Wherever f minus x is positive, f plus is 0. And vice versa. Well, when I say it's greater than 0, it includes the value plus infinity also, because I am talking about what is called extended real valued functions. Okay, so that's fine. Now we have mod f. So modulus of f so you have two relations there. The two relations are that f is equal to minus f minus mod f equal to minus. These are the two basic relation connecting f and mod f. Now if f is measurable, then both f plus and this we have proved earlier. That is, if f and g are two functions, then maximum of f comma g and minimum of f comma g are all measurable functions whenever f and g are measurable. So we are just using that side. Okay. And then of course you see that these relations are true. So f is measurable. We can write here, in fact strengthen this and write it as if and only if both f plus and f minus are true. Now we want to prove a theorem, a little result. Let f be a measurable function that is an extended real valued measurable function on. Then f plus and f minus are integrable on E if and only if mod f is integrable That's quite easy to prove. It only uses inequality and what you call for non-negative measurable functions. we have defined, or we have proved the monotonicity theorem. We make use of. Now recall, if be integrable, if this we have defined. We are going to use this result. So we prove the assume then f plus f minus r is integrable. By linearity of integral. That is minus, and which is less than. So mod f is integral. Conversely, in the convex, now what we have is this 0 less than or equal to f plus mod f, and now by monotonicity of the integral is less than or equal to finite and integral over E infinity. Okay. So we have seen that mod f plus and f minus, they are all integrable together. Okay. Now we are in a position to extend the definition of integral to general measurable functions. Now a measurable function f on E is said to be integrable if mod f is integrable. That means equivalently both f plus and f minus are integrable. Okay. By the previous theorem. Okay. Now we define integral of such functions. So definition, let one then integral of is defined as now there is no ambiguity about this definition because both integral f plus and f minus are finite. Therefore, this is well defined. Now, if integral f plus is plus infinity and integral f minus is also plus infinity, then we would be in difficulty because this won't be properly defined. Now, let me give an example of such a function. So, now you take E equal to R. Sin x. This is not integral. This is not integral. Okay, because you get integral of mod sin x to be plus infinity. So it is not integral. Also, plus infinity is not. Now, when you are working on a function like a non-negative function, we may also allow the integral to be plus infinity. There is no harm in it. But then you see that in this kind of cases, so this integral is not defined, and hence so this is the problem that comes. Okay, but then our basic definition of integral is for integrable functions, and it is given by integral over e of f plus minus integral over e of f minus. Now that is the definition. So we have now extended to the general case with some kind of caution. Now we also do a little bit of observation of the following fact, that certain properties are always given as almost everywhere. For instance, you say f is finite almost everywhere, which means the function fails to be finite on a set of measure 0. Okay. So we need not insist that f is defined everywhere. On a set of measures 0, some properties you can leave it as vague. Still, all these definitions and the theorems would be carried over. Okay, so let us just make mention of that. Integrable over it. Then f is finite almost everywhere on E. And for such functions, integral over E f is equal to integral over E slash E naught where E naught is a subset of E with measure of E naught equal to. So what we can assert is that f is finite almost everywhere if f is integrable. How do we come to this conclusion? Now the proof is very simple, straightforward. We have earlier proved that if f is integrable, if f is non-negative and integrable, then we have shown that the help of Chebyshev inequality, that is in the last section, that f is finite almost everywhere. So recall and f is measurable and integrable. That is integral over E is finite. Then almost everywhere. That means there may be a subset E naught of E where the function may take infinite values, but the measure of such collection of points is certainly equal to 0. That is the assumption that we are making. Now we are assuming that, see, mod f is integrable. F is integrable. That is the definition, which in turn implies you can apply this result, and the consequence is that mod f is finite almost everywhere. That means, what does it mean? It means the following, that is f plus and f minus are integrable, and hence finite almost everywhere. Therefore, what we have integral over E f is equal to integral over E f plus minus, and you see that this is equal to minus, where E naught plus is the set where Okay. And E naught minus is the set where and further what we have is the measure of so we have integral over E F F minus. And measure of E naught is equal to 0. That is clear. So this need not be need not be you know uh, what you call disjoint. Need not be disjoint. This is equal to 0 and therefore so when we develop general theory we can assume that f is integrable over E and f is finite everywhere. There is no harm. Okay, because you can always exclude a set of measure 0 whenever we take the integral. Doesn't matter. Okay. So this is something that we observe, and now henceforth we shall uh, assume that f is a measurable function on E. Okay, right. So let us work this. Now we make some remarks. So we immediately come to look at whether uh, the integration is a linear operation or not. So our problem is integral f plus g. Suppose both this equal to so this is one of the questions that we are asked. Okay, now there is a problem. The problem is alright. If both f and g are see, or I will make it more clear. Suppose at some x or vice versa. So f plus g will not be defined unambiguously. At x. This is a problem because it is going to be f of x plus f plus g of x is equal to fx plus gx, and if they take plus infinity and minus infinity or vice versa, it is not going to be defined. So there is a problem. Okay. So once you assume f and g are okay, f and g are integrable if assumed to be then f plus g may not be defined, fail to get defined only on a set of zero. Why? Because it is finite, both f and g are finite almost everywhere, which means f and g takes infinite values only on a set of measure 0. Okay, therefore it is there that you are likely to encounter this problem, that f plus g may not be defined. And this, of course, this set may be ignored while defining the integration. Because on this set, whatever happens, since the set of measures, it's a set of measures 0, so the contribution to the integral from that is going to be 0. So that doesn't matter. Okay. Therefore, we can, one way to get out of this kind of problems is that to assume both f and g are integrable functions. Now, this is a remark which has to be taken quite seriously. Now, you see that if A is the set on which where both fx or it is enough to consider only one of the 5, doesn't matter. Measure of zero whenever f and g are integrable. F and g are integrable. Then integral over E f plus g even if irrespective of what values one assigns for f plus g on E slash A, it is immaterial. For the so this is something that we should be aware of. Okay. This is totally so we shall assume we shall work on functions which are integrable. Okay. Now without loss of generality, we shall assume further remark without we shall assume that both finite that is in the light of this remark, because otherwise you are working on A, but the integral on E is the same as the integral over, so it doesn't matter in the context of integration. So this is our assumption. We assume that work on what are called the integrable functions. That is the assumption. So now we can verify that integration is a linear function. Let the functions f and g be integrable on P any alpha and beta the functions alpha f plus beta g is over E, and now let us prove this. I mean, it's not difficult to prove this, just simple thing, namely, of course, without loss of generality, we make the assumption that both f and g are finite on B. Okay. So we have so let us take the situation, assume alpha is positive. Take this case. Yes. And minus alpha sorry, what I wanted to say is this. We are considering this case. Okay. Further, if alpha is negative, then alpha f this is equal to minus alpha into f minus and this. Therefore, we shall do this. Now you see that is this one. You see that for alpha positive, so you see that alpha f This by definition is integral over E minus for alpha positive. So in any case, whether alpha is positive or negative, this is true. Okay. Therefore, we can expand this. So alpha positive is quite easy. For alpha positive, this is equal to this one. So this is equal to integral over E Now you see that for non-negative functions we have already defined this. This is equal to alpha this is equal to over E. What about negative? Alpha equal to 0, there is nothing to. This is equal to integral which is equal to minus alpha times integral over E minus alpha times minus 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 alpha times now this you can write as minus alpha, that is positive, therefore you can pull it out. This you can write as alpha times minus integral f minus that's equal to alpha times integral So alpha equal to 0, it is clear. So in that case it is equal to 0 times. So in all cases this condition is satisfied. Now what do we do? So that is that. So let us work. Now it is sufficient to show that G. is integrable and now you see that this is what you get. Mod f plus g mod g. That is there. Therefore, by monotonicity, we have and this of course is less than or equal to, this is by the result of the previous theorem. And each of them is finite, therefore this is finite. F plus g is integral. Now we shall assume the following. So you see that integral over E f plus g, by definition this is equal to integral over E plus minus integral over E minus. Now we know that by definition f plus g, and that's equal to only. Now that implies, in fact it is given only f plus g plus f minus plus g minus is equal to now we prove the following. By linearity, this is equal to yes. And similarly, integral over E plus. Now you see these two are equal. Since okay, now what we have is this. These are equal. Therefore, you see that get It's implies G minus, that is that completes the proof. Okay. Now we also prove the monotonicity, that is just one line. Let's prove the monotonicity and then stop case. Easy to prove the monotonicity. And nice. Then H is greater than or equal to 0. By linearity, we'll write it properly. Now here I want to make a remark that we are assuming f and g are finite on E. But essentially our assumption is that both f and g are integrable over E, which means that except on a set of measure 0, g and f are finite only. So on that. So by the previous remark that we have made, you see that it follows that G and F are finite on a subset A of E, and E slash A has measure 0. Okay. So without loss of generality, we can assume this, and the rest of the proof would work with A, and which is essentially the integral with. So see, without loss of generality, we can start with this assumption that G and F are finite. That's it. So with this remark, let me stop for the day, and we will continue with it at a later date. Thank you very much.